So let's start. So in the previous class, I very briefly just started introducing the problem of supervised learning. And prototypical examples of supervised learning are classification and regression, although these are not the only supervised learning problems, right? But we'll keep using these two problems as we go on for at least the first half or so of the course. So how do we model the supervised learning problem? So here's a mathematical model for this. We are given an unknown, we are given a relationship between a feature and a label. So this could be in the form of a function. It could be y equal to some f of x for some unknown function f. Or it could be specified in terms of an unknown joint distribution pxy. And this could either be discrete or it could be continuous. The goal is to design a learner which, given some sample data, is able to learn the relationship between x and y. Our goal is to first goal is to formalize this problem in a precise manner. So what we are given is a labeled data set. It consists of n pairs, where each pair is assumed to be independent and identically distributed according to this unknown distribution pxy. So this is all that we are given, and the goal is to design a predictor h, which takes x as input and outputs a label y, with the goal that h of x is as close to the true y as possible. All right, and for this, we'll choose a hypothesis class instead of always choosing h to be any arbitrary function. We'll restrict this to belong to some class of functions. Now, how we choose that particular class of functions is also a design choice, and we'll look at that design choice a little later. But given a hypothesis class h, a learning algorithm is one which takes this data set and the hypothesis class as input and outputs some predictor h which belongs to this hypothesis class. And the goal is to ensure that h of x predicts y correctly over an independent sample. To be a little more precise, we define a loss function, and we say that the learning algorithm is good if the population risk or the generalization error is small. The population risk or the generalization error is simply the expectation of the loss between the predictor output by our learning algorithm and the true value of y. Right? And this expectation is taken over a pair of random variables x and y, which are independent of the data set that is given to us, but has the same distribution as the data set. So that is going to be the assumption whenever I say a supervised learning problem. Now, all of these, keep in mind, all of these are assumptions, and in reality, there could be deviations from each of these assumptions. But in many cases, we'll assume that it's actually close to this. Now, in practice, you don't really know the true distribution pxy, so you evaluate or approximate this population risk by taking the empirical average of the loss over a separate test data set, which has the same distribution as your training data set. Right? So we looked at some special cases: binary classification, multi-class classification, and regression, and I'll keep bringing this up as we go along. And towards the end of the last class, we looked at some examples of learning problems. Right? We defined what the feature space is, what the label space is, what the hypothesis class is, and what the corresponding loss function is. Remember that whenever I say classification, it is always going to be with respect to the 0-1 loss. That's what we're going to evaluate it with respect to. Right? And we also defined the so-called feed-forward neural networks, which we'll be looking at in more detail as we go on in the course, which is just a sequence of compositions of linear transformations followed by component-wise nonlinearities, which are going to be called activations. So you should keep this in mind as we go through the course. We look at one other toy example, because all of these are a little more complicated, and we would like to visualize what happens with each element of the learning problem. So we'll look at a very toy example, and we look at each of the elements through this toy example. So again, let us consider a classification problem, a binary classification problem, where the feature space is simply the set of all reals. And since it's a binary classification problem, y is either 0 or 1. And the loss function is the 0, 1 loss. The hypothesis class that we are going to consider is the so-called step function. So it's h of x, which is equal to indicator that x is between some alpha and beta. Okay, so this is our hypothesis class. So all of our predictors visually look something like this. So this is the real line, and your predictor is 1 in a certain interval and 0 everywhere else. Okay, so each of our predictors in this hypothesis class looks like this. Now, for this particular predictor, let's also assume that the ground truth is drawn from this class. Okay, so we'll assume that the concept class is also h, which means that y is equal to f of x for some f which is in h. Okay, it's a strong assumption, but it's a toy example just to visualize what is happening throughout the learning algorithm. All right, so this is y equal to f of x, and where the distribution of x could be arbitrary. Okay, so x has some distribution px. Let me call this capital Px, which is unknown. Okay, and let's say that my f of x, since it belongs to this, since the concept class is equal to the hypothesis class, I can write f of x as indicator x lying between some alpha and beta. Let me call the true alpha and the true beta to be alpha star and beta star. So the ground truth is fully specified by these two numbers, alpha star and beta star. All right. So now let's say that we design some predictor which outputs this particular h of x. Or even otherwise, suppose we consider one particular predictor from this concept, from this hypothesis class, where h of x is indicator alpha less than or equal to x less than or equal to beta. Okay. Now, in this case, we'd like to understand And this alpha and beta could potentially be different from alpha star and beta star, right? So there could be a number of different scenarios where, let us say, this is the ground truth, and our predictor could be something like this. Both of them take the same value, but I'm writing one sort of below the other, just for easy visual distinction. So this is my alpha, and this is my beta. Now, say I pick an arbitrary alpha and beta, what would be the generalization error of this particular predictor? So what is R of H? I'm sorry? Why? What is the loss? So a more fundamental question is, in general, for a classification problem, what is the generalization error equal to? Correct. So the generalization error in a classification problem is simply the probability of incorrect classification. So in other words, this is just the probability that h of x is not equal to f of x, because there's no other randomness in the system except for x. Given x, y is already a function, because that's our assumption. And anyway, h of h is also a deterministic function. So the ground truth as well as our predictor are both deterministic. The only randomness comes from the feature vector which is drawn. So this is the probability that h of x is not equal to f of x, right? Can you give an expression or a description of this risk in terms of alpha star, alpha, beta star, and beta? So when do you incur an error? Probability that x belongs to alpha between alpha and beta. 1 minus, okay, you have to be a little more careful. It's 1 minus the probability that both of them match. So you're saying that the probability that they're equal is the probability that it lies in the interval alpha to beta star. Are you sure? Yeah, so you also make a correct decision if it is less than alpha star or greater than beta, right? So you make an error if you lie either in this interval. So you make an error if you lie in this particular interval or this particular interval. Right? So this is equal to the probability that x is either in alpha star up to alpha or between beta star and beta. So here are we assuming that alpha star to beta star and alpha to beta are overlapping. In this case, we're kind of assuming for this, it's actually valid only for this particular picture, right? Because it could be the case that, I mean, this is only one sort of special case, right? It could be that you predict a beta, or you predict a H which looks something like this. Right? In which case you make an error if, so let's say this is my alpha and this is my beta. I make an error if I'm between alpha and alpha star, or beta and beta, or beta and beta star. It could also be the case that they don't overlap at all, or it could be the case that one is a subset of the other. Right? So it's only in regions where, so another way to put it is this is equal to the probability let's say this is 1 minus the probability. So when is it correct? Can you give a general expression for when you make a correct classification? Can't say that, right? Can you say all of this in terms of set operations between the sets? Okay, so certainly if you're in the intersection between alpha star, beta star, then you're correct, right? But is this the only case? Okay. What do you mean union greater than B and less than alpha? So from which to infinity should I take? Okay. Again, can you maybe give that in terms of set operations? Okay. So in the region where they overlap, right, it is basically the intersection. Right? What about this? Yeah, complement intersection. Yeah. Which one? So okay. So when do you when is the classification correct? When both of them predict 0 or both of them predict 1. Correct? So probability that you're correct is equal to the probability that f of x is equal to h of x is equal to 0 plus the probability that f of x is equal to h of x is equal to 1. Right? Also, these two events are mutually exclusive. That is what we look at, right? So when do you say that f of x is equal to 0 and h of x is equal to 0? When is f of x equal to 0? Correct. So it's f of x is equal to 0 if x lies in alpha star beta star complement. And h of x is equal to 0 if it is in alpha beta complement. So this is the probability that x lies in the intersection between alpha star beta star complement intersection alpha beta complement plus, when is f of x equal to 1? When it's in alpha star beta star, and h of x is equal to 1 when it is in alpha beta, right? So this is x lies in alpha star beta star intersection alpha beta. Right? Any questions? Okay, which is essentially the same as what I had over here, except that you can write this union as a sum because they're actually mutually exclusive events. Right, so this is the probability that the classification is correct. So the population risk or the generalization error is simply 1 minus the probability that you're correct. Any questions? All right, so let's proceed. So it's good to keep this. We'll keep revisiting this example as we go along. So just keep this in mind. So again, remember that our goal is to design a learning algorithm which outputs a predictor, HS. I'll use this H subscript S to indicate that the predictor that you output depends on the data set. Because it's a function of the data set. And we want this predictor to have a very small population risk or a generalization error. Now, can we always do this? Is it possible to always achieve small population risk or generalization error for even a simple problem? It could be a very simple problem. Let's go back to the toy problem that we just discussed. Is it possible to design a learning algorithm for which we can achieve a small population risk? If yes, tell me why. If not, why not? What do you think? Just take a guess. Okay. Okay. Why so? So there's no linear classification going on here, right? It doesn't matter whether it is linearly separable or not. So to be take a concrete example, let's say that this is my problem, right? So it's indicator of closed intervals. That's okay. The goal is to design a learning algorithm that does well, even if you don't know the input distribution. Right? So for any input distribution, you should be able to. Okay, you're kind of getting there, but still not quite. Okay. So remember that in this special case, there is one predictor which achieves zero generalization error. It is h of x equal to f of x. Because we're assuming that we're operating with a concept class which is equal to the hypothesis class. Right? So there is one predictor which achieves zero generalization error or zero probability of error. The question is, can we always find it? Or can we find something that is very close to the ground truth? You can do whatever you want. I'm asking if there is some other fundamental impediment to finding this. I'll give you infinite compute. So for at least for this first discussion, we're assuming that you have infinite compute available to you. Don't worry about computation costs. What do you mean step size? So forget all what you know about gradient descent and everything else. You're allowed to optimize exactly. You frame an optimization problem, there is a black box which gives you the answer to that optimization problem instantly. That's the assumption for this first part, okay? So as I said, don't worry about computational complexity at all. Yes. Correct. So that's the problem, right? In our whole modeling, we've assumed that the training set is random. It is random and drawn IID according to PXY. Now, if it is random, it is also possible with some probability you get a really bad set. For example, let's say that all your entire data set consists of copies of the same point. All right, it is x1 comma y1, x1 comma y1, x1 comma y1, x1 comma y1, and so on. So all your n, you have n copies of the same sample, which is essentially worthless to you. All it tells you is whether that one point is 0 or 1, right? And that is the fundamental problem. Your training set is random, and therefore, for whatever predictor you design, your predictor itself is a random function, keep in mind, because it depends on the random training set. So essentially, if your training set is bad, then even the best learner can't do well. Right? So it's not possible to do well all the time. So we have to be a little careful in what we mean that a learning algorithm achieves a small population risk or a generalization error. Right? It's impossible for any learning algorithm to achieve a small generalization error all the time.
But you can choose the training set such that it follows the same distribution.
It is the same distribution. I agree. The distribution is the same. The problem is not with the distribution. The problem is in the randomness itself. There is some non-zero probability that you get a training set that is actually not very representative of your sample. So let me take the following example. So let's take coin tosses, right? Let's jump out of this exact problem for now, but something related. So suppose you have a coin, a biased coin, and your goal is to estimate the bias of the coin. That is the probability that you get a head. You take n tosses. You say that on an average, you're going to have roughly the number of heads is going to be roughly equal to the bias of the coin. But what does it mean when we say that the bias is going to roughly be equal to the number of heads? It's not that every time the bias is going to be, the number of heads is going to be close to the bias, right? With some non-zero probability, you could get all heads, even if it is a fair coin. The probability of that happening is very, very small as n becomes large. But the probability is non-zero, nevertheless.
What I'm saying is, if the bias is set on training,
Correct.
then you can choose the training set such that it is represented.
You can't choose, right? I'm saying that the training set is drawn randomly. That's the fundamental assumption that we made. Because otherwise, you're making additional assumptions on the training set. You're saying that the training set is not just random, it is also nice and allows us to learn F well enough. But that's not the case. But you're right that in most cases, with high probability, you're going to be able to do well if n is sufficiently large. So when you toss a coin n times and n is sufficiently large, with high probability, the fraction of heads is going to be close to the bias. But with some really small probability, it could be very different. That's the point that I'm trying to make. right? So with some even small probability, you could get a bad training set. So then what can we hope for? Because HS is itself random, and we need to account for the randomness in the training set itself. So let's maybe take a step back now and say what is the best that we can achieve. So given the best possible learning algorithm, is there are there fundamental limits that no learning algorithm can beat? So firstly, if we knew Pxy and there were no restrictions on h, you can choose any function you want. And fundamentally, you know, this is a very crucial assumption. You knew Pxy. Okay. Then the smallest possible population risk that you can achieve is equal to this quantity. It's the minimum of this particular loss, where this is minimized over all possible functions, h from x to y. So no predictor can give you a generalization error lower than this particular quantity, because it's assuming that because this predictor already knows the true value of Pxy. Okay, let's say that it's so this is the smallest population risk. It is possible that this is never achieved, right, for some weird class of loss functions. Okay, but more often than not, you can just assume that this is actually a minimum. Okay, so this minimum possible population risk is called the Bayes risk. And when this infimum is achieved, we'll say that the minimizing h we'll call it h subscript b. We'll call this the Bayes optimal predictor. Note that the Bayes optimal predictor is drawn for that specific Pxy, and therefore in general it's not realizable in practice. Okay, it's something that gives you a bound that it's no matter what you do, you can't do any better than this, right? Okay, but if we restrict ourselves to a particular concept class or a hypothesis class h, then the minimization has to be done not over all possible functions, but rather functions within the hypothesis class. So the minimum possible generalization error that we can achieve is going to be denoted R star of h. Say that this is the minimum generalization error from this class. Again, I'm putting infimum, but for convenience, you can just assume that these are minimum. And this minimum is achieved by some particular predictor. All right, but in practice, we don't really have Pxy. We only have the data set. So our goal is to somehow, so our target really is to design a learning algorithm which takes the data set as input and outputs a predictor that is in some sense achieves a generalization error that is as close to R star of h as possible. Right. So it's not.
So I have a question here actually.
Yes.
So if we know P of xy, right?
Correct.
How is it possible that we don't do correctly all the time? Because if we know the relationship.
Because even given x, y may not be a deterministic function of x. If y is a deterministic function of x, that is we are in the realizable setting, then we can achieve zero error or zero loss. But if you recall in the original formulation of our problem, we said that the joint distribution is known. So even if you know Pxy, given an x, y is still not deterministic. Y could be a random function of x. For example, if you want a concrete example, you could say that the true joint distribution is the following. X is randomly drawn according to some distribution, and y is equal to x plus some small amount of noise. Right? So even if you knew x, it's impossible to predict y exactly.
Okay.
Does that answer your question?
Yeah. So P of xy doesn't always. It's like it's still not the perfect ground truth.
Okay. When I say the perfect, yeah, I'm saying that there could be an additional source of randomness. Right? Does that
Yes.
answer your question?
Yeah.
So the setting that I guess you're referring to is the second case where we assume that y is equal to some function of x. In this case, if you know Pxy, essentially you know Px and you know f, in which case you can achieve zero error, and that problem becomes trivial.
Okay.
Right? So
Thank you.
the more general case is where given x, you never know y exactly. There's still some additional randomness. For example, there could be some hidden variable that you're not able to measure directly, and that accounts for this additional randomness in the system.
So it depends on the S actually again over here.
What do you mean depends on s? So s is assumed to be drawn according to Pxy.
Yes, yes. In that, even though we draw S from PXY, you're saying that there could be something that fails to represent Y.
Yeah. Even
Yeah.
if you know Pxy exactly, I mean, forget about the data set. If you know Pxy, then you don't need the data set. Right? I hope you agree
Yes,
with that
yes,
one. Because whatever additional information you don't get any additional information from S than if you have Pxy.
yes, yes. Agreed.
Right? The goal is to learn something about Pxy from S.
Yes.
All right. Any other questions?
Yeah, I'm good. Thank you.
Okay, thanks. Good. Yeah.
Special case,
Yes.
the base risk is always fundamental, which is zero.
The base risk is going to be zero. Assuming, of course, you have a nice enough loss function which says that it's equal, that the loss is equal to zero when y is equal to y hat. Right. You can always achieve y equal to y hat if you have a concept class. The base risk, yeah. But generally, we assume that the loss is such that L of y comma y hat, L of y comma y is equal to zero. Good. Any other questions? Right. So that's the main problem, right? If you knew Pxy, then the problem is kind of easy. I wouldn't say that it's a trivial problem because a lot of estimation theory is basically boils down to given Pxy, how do you choose the best predictor? And even that is not always an easy answer. Right? Even if you knew Pxy, getting the optimal risk is not always easy, particularly if you have computational constraints. Yeah. Yeah. How do you compute the expectation if you don't know Pxy? Right? This expectation is a function of Pxy, right? Okay, that's good. So that's really the bottleneck. We don't know Pxy, so we're not able to compute this expectation, and that is what prevents us from finding the best possible predictor. If we knew Pxy, then we can compute this expectation. The hard part is that we can't compute this expectation. Right? So now we have these two quantities, which are sort of lower bounds to the population risk that we can achieve. The base risk, which is the absolute minimum, even if you even if you chose H in the best possible way. And if you didn't know how to choose H and you chose one arbitrarily, then the minimum generalization error that you can achieve is this R star of H. So given a particular hypothesis class, let's say you picked 2-layer neural networks with these many hidden neurons, all right? Then this excess generalization error, that is the generalization error between any predictor output by the learning algorithm and the base optimal predictor, can be written in this form. Essentially, I've just added and subtracted R star of H. Okay. I've added and subtracted this for a very specific reason. If you look at this particular quantity, right, this quantity, this is what we call the approximation error. And this is the difference between the best possible predictor within H and the best possible predictor among all possible functions. All right. And if you think about it, this quantity over here doesn't depend on how we choose our learning algorithm. It depends only on how we chose the hypothesis class H. It's purely dependent on H. So if you chose a rich enough H, for example, if you chose H to be the class of all possible functions, then this approximation error would be exactly equal to 0. Right? But then if you chose it to be something else, maybe the true predictor is a polynomial, and instead you chose your hypothesis class to be the set of all linear or affine functions. So if you choose a linear function, a linear predictor, whereas the ground truth is actually polynomial, then you incur some amount of approximation error, particularly if it's a polynomial of degree greater than 1. So this approximation error is the error you incur because you chose a bad H, something that doesn't represent the actual ground truth. Right? Because even choosing H is a design choice that you have to make. All right. If you choose a neural network with some particular number of neurons and a certain number of layers, it can generate only so many functions. So it can't generate any function. Right? And that is the error, that is the excess risk that you have to pay for choosing that particular H. Now, having chosen a particular H, this particular quantity, which we'll call the estimation error, tells you the price you have to pay for choosing either a bad learning algorithm or for getting a bad data set. So if you think about it, this quantity essentially just depends on the hypothesis class. I mean, you've already fixed the hypothesis class, and it tells you how you are relative to the best H within your hypothesis class. Now, this quantity could be large if your data set is not representative enough, or you chose a bad learning algorithm. So both of these can lead to this estimation error being large.
So this R star of B, RB class can be written as R star of the concept class.
If it's a concept class, then R star of H is equal to RB star. Right? If you're in the realizable setting, then the approximation error is exactly equal to 0. So the approximation error is the penalty that you have to pay for not choosing the hypothesis class equal to the concept class, or if there is additional randomness left over. Okay. So the approximation error, as I said, it's small if H is kind of rich enough. if you take h to be the set of all functions, or if somehow you could choose h to be equal to the concept class, then this quantity is equal to 0, or you can make it as small as you want. And the estimation error depends on a lot of factors, but primarily based on the learning algorithm, and also depends on how you chose h, and also depends on whether you got a nice enough data set. Because remember, S is also a random quantity. Your data set is random, right? But as we'll see in a little bit, you can make the estimation error small if h is not too rich. So if your hypothesis class is too complex, then it's difficult to learn. If it's simple enough, then it's easier to learn. That's something you've probably already seen in your machine learning course, right? If your class is too rich, then there's a tendency to overfit, right? You will overfit the data, and the estimation and the corresponding estimation error will be large. But if your h is too simple, if your h is simple enough, then you can make this estimation error small, because you can learn the hypothesis class well enough. For example, if you take a linear classifier, you can learn a linear classifier well enough, but the problem is the approximation error will then be large, because your h is not large enough. So there is this trade-off between the approximation error and the estimation error. You choose a rich hypothesis class, the approximation error will be small, but the estimation error is potentially going to be very large, because you only have a limited data set. And correspondingly, if your h is too simple, then your estimation error then your approximation error will be very large, but your estimation error will be very small. So the whole goal behind machine learning is to delicately balance the approximation error and the estimation error. How do you choose a nice enough h that is easy to learn, but at the same time approximates the ground truth well enough? Right? And there are different ways of making the approximation error small. One is by choosing a rich enough class of functions that encompasses almost everything there is. The other is if you already have some information, some prior information about the ground truth. For example, somehow you got to know that your ground truth is going to be a low degree polynomial. Then you could choose your hypothesis class suitably, right, as the set of all polynomials of a certain degree, right? Which is what happens in practice. For example, if you want to design an image classifier, there are certain features about images that you can use to build your hypothesis class. It's one of the reasons why, for example, convolutional neural networks work better than simple feed-forward neural networks, because feed-forward neural networks turn out to be a much larger hypothesis class and too complex. But convolutional neural networks are sort of smaller, simpler hypothesis classes, and they give a delicate balance between the approximation error and the estimation error. Right? So these are intuitions that we'll keep using as we go along the course. Any questions? All right. So as I said, the recurring theme in this particular course is how do you balance these two quantities? How should we choose h, which in some way corresponds to what I call an inductive bias, what you know about the problem, or what kind of structure you impose on your hypothesis class, on the class of predictors that you choose. And the second problem is, okay, having chosen a particular h, how do you learn h efficiently? That is, you want to achieve a generalization error that is close to the best in the class. And we'll kind of treat this as two independent problems, more or less. So for a given h, we want to learn h efficiently, and then we'll separate that out from the problem of choosing a particular h itself. And when we say we want to learn h efficiently, we want a learning algorithm that is computationally efficient. All right. Okay, so now, as I said earlier, the predictor that you choose, your predictor, your learning algorithm, takes the data set and the hypothesis class as input and outputs a predictor HS, which depends on the data set. Now, if the data set itself is random, then the predictor that is output by the learning algorithm is also random, and it's impossible to do well all the time. So how do we mathematically say what is a good learning algorithm? Because we want to strip out all of the other details and we want to say when does a learning algorithm work well, right? So we'll say that a particular hypothesis class is learnable or efficient, in some sense efficiently learnable. The correct term, the terminology that we'll use is probably approximately correctly learnable. If essentially what you can do is ensure that the predictor output by our learning algorithm is close to the best in the class with high probability, right? With high probability over the training data set because of the randomness in the data set. So if you look at this particular quantity, the probability that the generalization error achieved by our learning algorithm is less than or equal to the best in the class plus some small epsilon. And this probability is taken over S. This quantity is a fully deterministic quantity. It depends on Pxy. So that's something to be kept in mind. But it's still something, there's no randomness involved anymore. Right? So this is a deterministic quantity that depends on Pxy, your learning algorithm, and H. So we want this probability to be greater than or equal to 1 minus delta for all Pxy. Maybe that's not. So irrespective of what the ground truth distribution is, I want to ensure that I can do close to the best in the class with high probability. If I can do that using a finite number of samples, so there is some, for a given epsilon and delta, there is some n of epsilon and delta, such that if I have more than n of epsilon delta many samples, then I can achieve this epsilon delta error. With probability at least 1 minus delta, I can achieve a generalization error that is epsilon close to the best in the class. And the minimum number of samples in order to achieve a particular epsilon delta error, that's what we'll call the sample complexity of that hypothesis class. All right. Any questions related to this particular definition? Okay, so just to understand why this sample complexity could be small or large, let's take one particular example. Say the set of all polynomials. Okay. Yeah. Yes.
Epsilon and delta values are defined by the user or whoever is training.
Sort of. Let's say that this is the target epsilon and delta error that you want to achieve. But I mean, this is a definition. So the hypothesis class is PAC learnable if you can achieve this using finitely many samples for every epsilon and delta. So if somebody gives you any target epsilon and delta, you have to tell me what is the minimum number of samples you require in order to get that epsilon delta error. And there is some bound on n of epsilon comma delta. If you can't do it using finitely many samples, if you cannot achieve an epsilon delta error using any finite number of samples, then we say that that particular hypothesis class is not PAC learnable. right? Now, just to develop a little more intuition, let's assume that we have a concept class. Let's say that I have a concept class H, which is the set of all polynomials of degree, say, k. Let's specifically take and let us say that we're dealing with a regression problem, not a classification problem, right? Because classification will pose additional challenges. Right? So this is our concept class as well as our hypothesis class. So we know that the ground truth is coming from this particular set, and we're trying to pick one function from this particular set. And whatever, you can say that the loss function is L of y hat is maybe the squared error loss. So here's my question to you. Is it possible to achieve zero loss? That is, I want to achieve a mean squared error which is equal to 0.
As we are taking concept as a hypothesis, let's say.
Okay. Why?
Because the
Approximation error is 0. Fine. Can you, okay, so let me pose it a little differently. Can you give me an explicit learning algorithm that can achieve zero estimation error or zero generalization error? I should have made that more precise.
it will not be zero because
Mhm.
loss function is a square function.
Okay.
Every time, like once, like a positive fraction, the loss function, it reaches up to zero, but it does not become zero.
Why not? If let's say that f of x is equal to h of x, right? Then the output is the same every time, right? So I can, it is possible to achieve zero if I know the exact polynomial. Someone told me that, okay, the ground truth polynomial, let's say that f of x is summation I equal to 0 to k. Sorry, this should have, the summation should run only up to k. There are k plus 1 terms. This is ai, let's say ai star x to the power I. And somehow I got to know all of these AI stars. Then I can achieve zero generalization error, right? But is it possible to come up with a learning algorithm that is, at least in most cases, guaranteed to achieve zero generalization error? How many people think that it is possible?
Why can't, if we have infinite complete, why can't we iterate over all the hypothesis class elements?
How many elements are there in the hypothesis class? Again, what do you iterate over, right? You're only given samples, right? Okay, how many samples would you need? Okay, I say that you don't. This is a very simple problem. Again, I would suggest that you forget everything that you know about machine learning and then think of this as a simple high school problem. Yeah? You don't need roots. Basic linear algebra is enough. That's a big hint. What I'm saying is that all you need is basic linear algebra to answer this question. So given a set of samples, again, remember you have labeled pairs. You know what you're given are x1, x2, x3 up to xn, and f of x1, f of x2, f of x3 up to f of xn. Right? Now, using this, can you tell me if you can recover f from these labeled pairs? Yep. Yeah, as long as you have k plus 1 distinct samples, you can directly find all the coefficients of the polynomial, right? So evaluating the polynomial at k plus 1 distinct points is enough to recover all of the k plus 1 coefficients. And how would you do that? What would be the complexity of finding the coefficients? How do you find the coefficients of Yep. So you just construct the matrix of so it's just order KQ, right? So given essentially what you're given are xi. Let me call it something else. Say xj, f of xj for j ranging from 1 up to n. In fact, k plus 1 distinct samples suffice. So you construct the following coefficient or the following matrix, which is 1 x1 x1 square up to x1 power k, and so on 1 x k plus 1 x k plus 1 square, and so on up to x k plus 1 to the power k. And the following vector, let's call it a, which is 1 a 1 a0 a1 up to ak. So if what you know, because there's no additional randomness in y given x, you have f of x essentially f of x1 up to f of x k plus 1 can be written as the matrix x times the vector a. Right? So now the goal is to find a. And you can find a if as long as the matrix x is invertible. And this particular matrix, if you've seen it in linear algebra, this is what is called a van der Waals matrix, because every column is basically, so the first column is all ones. It's vector x power 0. This is vector x power 1, vector x power 2, and so on. So as long as x1 up to xk plus 1 are all distinct, this is going to be invertible. Right? And the computational complexity of inverting this matrix is order kq. So in this case, as long as your distribution is nice enough, that's one thing to keep in mind. Right? For example, if x is a continuous distribution, then essentially with probability 1, you're going to get k plus 1 distinct points. It's possible that you have a weird enough distribution that always outputs 1 point with probability 1. But for most distributions, you will be able to achieve 0 generalization error. And essentially, the sample complexity is just going to be k plus 1 for 0 error. If you can tolerate some more error, then yeah, maybe you need less than k plus 1 samples. So as long as we're restricting ourselves to, say, continuous distributions, our n of 0 delta is essentially k plus 1. Now, this highlights 2 points. One, that is, if you fix a particular k, then you don't need too many samples. You just need k plus 1 samples. But again, what if k is infinite? That is, you look at all possible polynomials. The concept class consists of all possible polynomials. Then what can you do? Is it possible to achieve a small enough generalization error? That becomes non-trivial. So clearly, at least hopefully at this point, you agree that the set of all polynomials of degree at most k is PAC learnable. Again, here I'm referring to this regression problem. I'm not talking about the corresponding classification problem. Because in the classification problem, I would have h of x to be indicator this quantity greater than or equal to 0. And in the classification problem, you get a little less information because you don't get to know the value of the polynomial itself. You only get to know whether that polynomial is greater than 0 or less than 0, which could potentially be a much harder problem. So you can't really recover A exactly. In this case, you can recover A exactly in this regression problem. So it's an easier problem to handle. All right. So the first sort of negative result that we see is that not all hypothesis classes are PAC learnable. So that's something unfortunate for us. If we had the case that all hypothesis classes are PAC learnable, then it's just a matter of collecting enough data. If something is PAC learnable, then it means that if you have enough data samples, then you can achieve small enough epsilon delta error. But life is not nice. So you have to live with the fact that not all hypothesis classes are PAC learnable. So there is this theorem. Again, we won't prove all of these, but I'll give you references. So it says that it's called a no free lunch theorem, and there are many variants of the no free lunch theorem, both here in machine learning and many other areas. So it basically says that there is no free lunch. You can't get everything for free. There is some price that you have to pay. It says that if you have a learning algorithm, so consider the best possible learning algorithm, taking how much ever compute you want for a binary classification problem. That's one of the simplest things that we can think about. Over a finite x, so our feature space is finite. That is also simplified. And we are looking at the 0-1 loss, but h is the set of all possible functions from x to y. So x is finite, and h is the hypothesis class, is the set of all possible functions from x to y, which means that h is also finite, right? Because how many possible functions do you have from a finite x to 0, 1? Correct. It's just 2 to the power cardinality of x. You can independently label each point either 0 or 1. So for each, you have 2 choices, and you have cardinality x many elements. So you have 2 to the cardinality of x possible labelings. So the no-free-lunch theorem says that if the number of samples that you have is less than half of the cardinality of x, it seems very specialized, but it has a lot of utility. So if you have not enough samples, if the number of samples is less than cardinality of x by 2, then there is some distribution and some concept or some ground truth such that the probability that the generalization achieved, the generalization error achieved by the best possible predictor, which takes n samples as input, is greater than 1 by 8 with probability at least 1 by 7. So this basically says that if the number of samples is less than half of the cardinality of x, then the generalization, then you cannot achieve arbitrarily small epsilon and delta. So you can't achieve an epsilon less than 1 by 8 with delta less than whatever 6 by 7. All right. Okay, there is a proof of this, but we won't be able to cover this. I'll just give a reference. Again, if you want to learn more about all of this, you'll have to take a separate course on statistical learning theory. But let's just take this for now. This is mainly to illustrate that, look, you need enough samples. So firstly, you need enough samples in order to achieve an arbitrarily small epsilon and delta error. In particular, if you choose an epsilon less than 1 by 8 and delta less than 1 by 7, then it is not possible to achieve this if n is smaller than cardinality of x by 2. That's one point. And this is essentially a tool which is used to derive more general results. It seems like very specialized because h is finite, x is finite, and it's for this particular number of samples and for particular this 1 by 8 and 1 by 7. But it can be used to derive results on more general h and more general x. But also a point that I want to make is that even if x is finite or even discrete, this problem is not easy. Because let's say, what does this theorem tell us if x is infinite and h is the set of all possible functions? So even if the cardinality of x is, even if x is countably infinite, forget uncountably infinite, and h is the set of all functions. So you have a concept class, not even a general pxy, which is even harder, right? Is it PAC learnable? It is not, right? The no-free-lunch theorem says that you need at least half of the cardinality of x to achieve an arbitrarily small epsilon delta error. It doesn't say that you can achieve an arbitrarily small epsilon delta error. It says that if you have less than cardinality of x by 2, then you cannot. So it's a negative result. So this says that if the cardinality of x is infinite and h is the set of all functions, then it's not PAC learnable. Because essentially what happens is that if h is the set, your class of functions is too rich, so no matter which learning algorithm you choose, it is going to overfit, and there is going to be some distribution for which, some ground truth for which you achieve an arbitrarily large error. right? So that's a fundamental limitation. And again, this is posed only for binary classification, but similar things happen both for regression as well as multi-class classification. So then what is it about the hypothesis class that determines whether it is PAC learnable or not? Because in the end, if we want to, there are two, as I said, there are two problems, right? One is how do you choose the hypothesis class? And given a hypothesis class, how do you choose the learning algorithm? If your hypothesis class is not PAC learnable, then essentially no learning algorithm can do it. There's no point in trying to look for a learning algorithm itself. So the first point is to choose a good hypothesis class which is PAC learnable. So when is a hypothesis class PAC learnable? Right? So that's what we'll try to address. And one thing to note is that in the setting of the no free lunch theorem, there is one predictor that can achieve R of h equal to 0, the ground truth predictor. Right? It is just that the hypothesis class itself is so rich that you're unable to find this particular predictor if the number of samples is not large enough. Right? So for any classification problem, if the cardinality of x is infinite and h is the set of all functions, then no learning algorithm can achieve arbitrarily small epsilon delta error. So if you're dealing with binary classification and your input space or feature space is infinite, then you have to restrict yourself to some small subset of functions. You cannot take h to be all possible functions. So you have to be careful. And even if x is finite, you need enough samples. All right. So as I said, although this theorem seems very specific, it can be used to derive much more general results. So this naturally, you get the following question. Look, if the cardinality of x is infinite, then how do you choose h? How do you choose h? Or is it that if the number of functions, clearly if the number of functions is finite, then maybe you can somehow search through all possible functions and find the best one. But what if the number of, if your hypothesis class is infinite? Is it possible to learn? It turns out that in many cases you can learn even if the number of functions is infinite and cardinality of x is infinite. But it kind of depends on how complex this class of functions is. And we'll see how do you measure complexity in just a little. All right. So one thing that which is not very hard to derive is the following, that finite hypothesis classes are PAC learnable. So irrespective of what the feature space is, even if x is infinite, if the number of functions in your hypothesis class, the number of predictors in your hypothesis class is finite, then if you have enough number of samples, you can achieve arbitrarily small epsilon delta error. And the proof is, again, not very hard. And I leave a lot of the details as an exercise. So basically, what you want to do is you want to find this h star, which minimizes the expected loss. Right? That's always our main goal. And we don't know pxy. That's the crucial point. So what is the next best thing we can do? Any suggestions? What could we do? We don't know this expectation. We can't compute this expectation because we don't know pxy, but we have samples which are drawn IID. So instead of minimizing this function, can we choose a h which minimizes some other function, which hopefully approximates this expectation? Y log. Again, you don't know expectation, right? You can't compute the expectation. So okay, here's a simpler question. Can we approximate this expectation by something else? So you can just you can try to approximate this ensemble average by a sample average. So instead of minimizing the population risk, you try to minimize this so-called empirical risk, where you take 1 over n times summation I equal to 1 to n, the loss function computed over these individual samples. So in other words, you have this training data set, you look at the average loss over this particular training data set and you try to minimize this. This is what is called empirical risk minimization. And this is essentially the workhorse of almost all supervised machine learning algorithms. Right? In fact, even other learning problems, you try to minimize some form of empirical risk or a variant of the empirical risk. So you have the data, you can try to approximate this. Hopefully, if n is large enough, then this quantity is going to approximate this expectation. Okay. So for a given h, the empirical risk is going to be a good approximation of the average risk or the population risk. And you can prove that ERM is in fact a PAC learner for any finite hypothesis class. Okay. So how do we prove that this happens? The first step of the proof is to essentially show that you fix any particular h. If I fix a particular epsilon prime greater than 0, you show that the sample risk or the empirical risk is close to the generalization error for h with high probability. So the probability that this deviates by an amount epsilon prime is less than or equal to some sufficiently small quantity. And it's not too hard to do this. You just use something like a Chernoff bound, right? Because if you look at this particular quantity, this is 1 over n times summation I equal to 1 to n L of h of xi comma yi. The xi yi's are all IID. So if you treat this as a random variable, let's call this zi. The zi's are all IID random variables, and what you're doing is you're just taking the empirical average. So these are IID. You can just use a Chernoff type bound to get this inequality. In particular, you can just do this for the 0-1 loss for classification because it's easy, because then this loss is either 0 or 1. It's whether it's correct or whether it's incorrect. And these zi's are therefore IID Bernoulli random variables. And you can just use the Chernoff bound for Bernoulli random variables. If you don't even want to go through the Chernoff bound approach, you can always use either Markov's inequality or the Chebyshev inequality for any random variable. That's much easier. All right, so that part is easy. And this is for one particular h. All this says is that if you fix a h, then the empirical risk is close to the generalization error for that particular h. It doesn't tell you that these two are close for every h. Right? To show that they're close for every h, you just do this using a union bound. The probability that this deviation is large for even one of those predictors in your hypothesis class can be upper bounded by the union bound, and you get this is less than or equal to the size of h times this quantity. Right? And that's all there is. That is all there is to derive a bound on the sample complexity. But one thing to keep in mind is that this approach doesn't work if h is infinite. All right, because this union bound gives you a trivial infinite upper bound. So then for infinite hypothesis classes, you need to do something more clever. Okay, I guess we're close to time. So let's stop here. Are there any questions?